Hi. Since the last video I helped cut down a 40-foot tree by hand, completely reorganized and rearranged the workspace in my office here, and have had the office suite next to mine be under construction, being both loud and playing breaker roulette, which has made it pretty difficult for me to make any videos since the last time I have worked here. So today we're gonna do something real simple, and we're gonna look at using GPIB enabled test equipment on a modern Linux computer, because this is something that I've been wanting to talk about for a while, and I'm finally at a point where I feel like I can just talk about this, and hopefully in the near future this is going to be a lot easier than what I'm going to show you how to do today, because it has finally been added into the Linux kernel about a week ago. So this is hopefully only going to get easier from here. Let's start out by just showing you what exactly I'm talking about here. This is an HP 34401A multimeter, and I have it connected to my laptop here over USB, going back to a GPIB port on here. I'll cover what all that means in a moment, but the gist of it is I'm measuring a resistor here that is 220 ohms, and I'm able to read that value over on my computer. Now, this is not the first time I've shown this concept or this device doing this on this channel. Way back when, before I even stopped using hex numbering for videos, I did a video on using my HP86 with this device to do some data logging of a thermistor while I was trying to measure the efficacy of a cooler for an LED light that I was making. Now, that gives you an idea of not only how powerful this is, but how old it is as well, because what I'm using to do this is an interface called GPIB. This is a GPIB cable, or HPIB, depending on how you look at it. This is a daisy chainable pass-through connector interface standard that HP designed for their computers and test equipment. They later released this to the IEEE, which became standard 488 and was used by other manufacturers and devices. The Commodore PET has a GPIB port on it, for example, although it uses a card edge connector, but you can get it adapted to cables like this, which is how you connect the disk drive to it. Now, the multimeter I have here is an HP 34401A, but we will look at using a couple other devices with this today. And around the back, we can see the GPIB or GPIB connector here. There's also RS-232 serial, which was added for this model, but GPIB's really what makes this special to me. Now, this laptop over here doesn't exactly have a GPIB port, and that's where this device comes in handy. This is a National Instruments GPIB USB HS. It's a USB GPIB adapter, and you can just straight up plug this in and bam, just read from it. But as we'll also see later, you can also plug this into a cable like this, which allows you to read from multiple GPIB devices through one interface. GPIB is an addressable bus. When I turn on this 34401A, it says its address right on the screen. We can also go into the configuration menu and bring that up again here. 11 is the address for this multimeter, and I can go through here and change this to another value if I want, but I'm going to go ahead and leave it on 11 for now. Now, this addressing is important because, well, here are 4 more GPIB addressable devices. I have these addressed as 6, 7, 12, and 13, which means one set of cables could be connected to all of these, and a single host could access every single one of them. Now, the kinds of hosts these were originally designed to be used with are definitely a little bit older than the Linux and USB adapter that I have here. If we look in the manual for the 34401A, we can see HP Basic as well as Quick Basic for DOS. Now, to give you an idea of how old some of this is here, here's an HP Basic guide from 1971. This has been around for quite some time. Here's another example with an HP 1981 Electronics Instruments and Systems catalog here that has a whole section for HPIB. And if we flip to the voltmeters here, we can see this HP 3438A HPIB equipped multimeter. Again, 1981. Now, why bother calling out how old all of this stuff is? Well, 1981 was over 4 decades ago, and this thing is over 2 decades old. But still today, you can buy multimeters from places like Keysight, Tektronix, and BK Precision that have GPIB as an option, because GPIB is that good. Now, I've been standardizing all of my equipment around GPIB because it's so good, and today I finally want to go over what it's like using all of this equipment like this, even though a lot of this is very old. These are much closer to the 1981 catalog than this is, but they all still work just fine and are really useful today. Let me go over what I have here. This is an HP 16500C logic analysis mainframe system, and we won't be using that today because it's actually a complete nightmare to work with over GPIB, and it's really complicated. That's a whole other topic on its own. Here we have an HP 6632A, and below it is a 6633A. These are power supplies that have different current and voltage ranges based on their model, which makes them both uniquely suited to different applications, but they are functionally identical elsewise. Over here, we have two HP 3478As. These are the predecessor multimeters to the 34401A here. All of these can be configured and communicated with over GPIB, but every single one of these does it in a slightly different way. Now, not to give HP all of the credit, this is a Tektronix TDS320 oscilloscope, and it is also GPIB enabled. Though, again, oscilloscopes and GPIB are really complicated to use unless you know exactly what you want to do with it, so we're going to leave that out here today as well. But for now, let's take the 34401A back over to the Linux computer, and I'll show you how you can set this up and use it yourself. So you have your GPIB enabled device and you want to connect it to a computer. It wasn't that common for computers to have GPIB, so you almost always needed an adapter of some kind. Right now, I am using the USB adapter that I mentioned, but these existed for pretty much all periods of computing history. Here is an 8-bit ISA GPIB interface card. Here's a 16-bit ISA GPIB interface card, and there were PCI and I'm sure PCIe ones as well. Now, if you want to go the vintage route, you kind of need to know what you're getting and make sure you can get drivers for it, and you need to make sure you avoid something like this, because you don't want it unless you know you want it, because this is a testing management card that basically runs its own code for controlling the test equipment directly. You don't just read data into and out of your devices to your computer directly. This thing acts as a whole man in the middle type thing, which can be really cool, but if you don't want that, then you really don't want that. Also, this thing's insane. I really need to make a video about it at some point because it's ridiculously cool. Now, these are all host interfaces, but you can also get adapters. This is GPIB to RS-232 bidirectionally. Now, whether or not something like this will work depends on your use case, because RS-232 is not an addressable bus. So in the configuration that I have this set up now, this will only access one single GPIB address through this port. So it's not optimal for every use case. Now, I believe there's also an Arduino-based GPIB adapter project that you can build yourself that would be fairly similar to that serial to GPIB adapter. I don't personally have a need to build one of those, so I haven't tried it, but that would definitely be an option worth looking into as well. For today's video, though, we are just going to focus on this device, which is a National Instruments device, but I'll clarify for those of you who may know, we're not touching Visa today. National Instruments devices like the one I'm using here are very popular because NI has a lot of support for stuff, but that's not out of altruism. National Instruments' whole business is products like this. This is LabVIEW. It's an ancient LabVIEW for 311, but it is a National Instruments product. This is a software environment that allows you to design GUI interfaces and control test equipment, and it's really cool, but very expensive to get into unless you find an ancient version like this. And that's what they really want you using. Now, you can just get the NI drivers for Linux here, which is a little weird because when I looked it up generically, it looks like the Windows drivers are $200. Yeah, I'm not sure what's going on there, but this kind of weirdness is why we're just gonna avoid NI in general. What we're going to use is this, the Linux GPIB package. This is an open source driver for Linux that works with GPIB hardware, including the NI GPIB USB HS that I have. The only problem is that installing this is just terrible and annoying to maintain. This is kind of like the CM153 cloning where I said, hey, in the near future, you won't have to use a weird hacky workaround to reverse engineer cards with a transparent window overlaid. Yeah, in the near future, you shouldn't have to do this horrible kernel module nonsense to use your GPIB devices, because newer kernel modules will do all of this for you, hopefully. But let me show you how you currently have to do this with this thing, because once you've downloaded the current version of the Linux drivers, you'll get two folders like this in here that are the kernel and user drivers. This is a little weird, but you're going to have to install both of these every single time your kernel updates, unless you want to figure out how to write a DKMS module for it. Now, if you've done anything in this previously, you'll want to run make clean to start, and since I have installed this stuff, I should. But with a clean or the initial state directory, all you have to do for the kernel is just run make to compile the drivers. Although you are going to potentially have to install a bunch of dependencies, I think it was Flex and Bison and AutoMake, your compiler will warn you about the different things as you try and compile it if you're missing anything. Now, after it's done compiling, we'll need to run make install, which will copy the files where they're needed, but you will need root permission for that. And those drivers are now ready. Now on to the user side, which is more complicated. Now, you should probably look at the install document, which will tell you how to do this. The first thing we're going to need to do is run the configure script, which I don't think needs the parameter, but they have it there, so we'll just leave it. And after that, you can run make, followed by the make install. And there we are, not quite done. That's everything that this repo will tell you how to do, but there's still a couple more things that we need to do. The first thing we need to do after this is group add GPIB. Now, I've already run that, so I'm not going to run it again, but I'll show you why you need that. For the GPIB devices that get added by the driver, you'll see that they all belong to the group GPIB. This group doesn't get added by the driver, but it is used by the driver, so you will need to add it. And then you'll also need to do the user mod -a capital G GPIB user to add yourself to the GPIB group, which again, I've already done, but that is another critical step. Now, after installing both drivers, creating the group and adding yourself to it, you're still not done because you need to run a command gpib config. But when you try to run it, you'll find that it doesn't work because it's missing a gpib shared object. What you have to do is run ld config, but again, we need to do it with root permissions. This will set up all of the libraries so that the programs know where they are. After that, you are free to run the gpib config tool. Though, you need to know which module that you're using. If you're using a USB one like I am, then this is the command that you'll need. I put this in a bash script so that I can just run that without having to remember this. But this is the device type that you're trying to activate, and you'll need to make sure that you have that set up correctly. Now, one more annoying thing about this driver is that you're going to have to run this command every single time you reboot your computer. But that's the last obnoxious thing about this, thankfully. Well, aside from when you're doing actual programming, but that's just other weirdness. Speaking of which, we're done. It's set up. We can finally do some programming. So let me show you how I am doing this and some of the different ways that you can. Inside the driver are a handful of different APIs for different languages. I am going to be using Python for this because Python feels like the modern day version of BASIC. It's a simple scripting language that is really powerful. The GPIB Python module here maps the C drivers and allows you to access the devices much more easily. All right, let's start out in just the interpreter here. So we're going to import GPIB. From here, we're going to create a device object that is an instance of the gpib.gpib class. Now, we need to specify two addresses here. If you have one single host interface, you're going to use 0 here. Then you need to specify the device address. As we saw, my 34401A is address 11. So we're going to go ahead and use that. We now have a device that represents the 34401A here. From here, we can send it a command using the write function. Now, what exactly you want to send to the device is going to be dependent on that device itself. Not a single one of the devices I have here has a similar command set to any of the other ones, even when they come from HP themselves. So this can be highly variable, and you're definitely going to have to look in the manuals. Now, the 34401A here uses SCPI, which is the Simple Command Protocol interface. I don't remember. But I do know if we want to just read what is on the display, we can just send the read command followed by a question mark, which tells it we're going to want a value back. If we send that, we'll see that the multimeter has frozen now and is in remote mode. From here, we can do a print and then a dev.read, and we will get the results from the multimeter. Now, annoyingly, it's always returned as scientific notation for some reason. I don't get this. It seems like every single one of my devices do this. So in Python, and this is one of the reasons why I like Python for this, what you can do to make this less stupid, you can cast this as a float, and that will handle the string interpretation here. But this won't work because we're going to have to rerun the read command that we actually wrote to the device before we can do this. So I'm going to do a Control-C. It failed because it never got any data. So we're going to send the read command again. Then we'll try and read data from the multimeter. There we go. Now this is meaningless because I have a resistor connected to this. So let's switch this over to 2-wire mode. Oh, we can't. That's because the device is in remote mode, which locks the front panel. Now, there's a button on the front for this, but the next time you go to read something, it's gonna be locked up again. It is possible to program it to not lock up, though. To do this, we're going to send the dev.ib, which I'm guessing stands for interface bus, local command. This will drop the multimeter back into local mode without having to press the front panel button for that. From here, we can then switch into the 2-wire resistance measurement. All right, after wiggling my probes, we can see that this is at 220 ohms, which is what the resistor is. Back on the computer, we can send the read command, then read the data in, and we can see our resistor value there. Now, you'll note that I have a bunch of stuff in my command history there, and that's because this multimeter acts a little weird. If we try to send the command and then send the command again, you'll hear it beep in an error. If we check the errors on the machine itself, which we can do in the menus somewhere down in here, blah, blah, blah. We'll see it's minus 410. What that means is it has data in the output buffer that hasn't been read by the host yet. And if it tries to execute the command that it was sent, it will clobber that data. I don't know why it doesn't just clobber the data. You might be able to configure it to do that. The SCPI command stuff is insanely complicated, so it wouldn't surprise me. But if you don't read the data every time you send it a command, yeah, you'll get that error. Now you can start to see the beginnings of how this can be useful. So let's do a very simple data logging application. Let's make a while loop. Let's bring up our command to read, and then our command to print. And if we let that run, we'll see we're reading in the value of the resistor constantly here. Now, this is probably the most barbaric way of using this multimeter. The way they are actually intended to use it is like, let's say we want to do a voltage measurement. You're supposed to do conf volt and then a range like 0.01 to 1 or 10 or something like that. I don't remember how to set the range, but you're supposed to do a complicated command like that to switch it to voltage mode, and then you'll take a measurement like that. And the reason that you do a measurement is that allows you to set the trigger of when it will actually take the sample. Now that use case is much better suited towards a properly set up experiment or test like the capacitor reforming that I did. But the use case I have today, I want it to be free running, where the trigger is not handled by the computer and the device just operates on its own. So let's take a look at how I'm doing that, because I've written a more complicated program that uses a Python web server module that allows me to get fancy graphics for this stuff and read any number of arbitrary devices that I have connected all at once. All right, I've moved the HP 34401A back over here with all of the other equipment, and I have connected it with the GPIB cable to the rest of the devices. Over here, I have a single cable that connects everything over there, and I can just plug this directly into my National Instruments USB adapter, And now I'm connected to all of those. Now over here, let's start taking a look at the code that I've been writing that allows me to do a little more complicated stuff with this. This is a class I've written for the 34401A that just has the basic commands to be able to read from it. There are a couple of things that I'll get into here in a moment that are a little weird, but basically all this does is every time I want to update the reading from the multimeter, it sends the read command and then reads back the data and converts it into a float that it stores. This is my main loop program that reads from a bunch of different devices all at once. We'll get into how these work one at a time. And here we can see the 34401A being read and having the device data hosted. Unless the reading is none. There's a good reason I've done this. Let me actually start the program here and you'll see why. I have two things here. We're going to go ahead and go to Window, and I'm going to walk over and turn on the 34401A here. And over on the computer, we can see the readings from the multimeter popping up. This is where this gets really, really cool. Now, I don't want to delve too deep into how I did the web stuff because that's going to be dependent on how you want to build a web interface. But to make a long story short here, I am sending a JSON object that has all of the data for every single device here. And when that data exists, it builds a little window like this that has the readings from the devices. When the devices are off, the GPIB interface will time out because it doesn't get a response. And this is where this comes into play. But let's start out by taking a look at an HP 3478A first. I'm going to go back over to the web interface, walk on over to here, and turn one of these on. After that turns on, bam, you'll see it pops up in the web display as well because it's now being accessed. However, the 3478A is a little different because when you're trying to read from it, you can just straight up read the buffer and it will always have what is currently on the display in the buffer, which is really nice and way better suited to my application here than the 34401A. The 3478A, though, is a lot more responsive. The 34401A needs a 1 second timeout, or else when you normally try to read the data, it will not respond quick enough and it'll seem like it's not there. Every single other device here is at least 10 times faster, which is really weird and annoying because I have to have the timeout slow down to 1 second for just the 34401A and then bring it back to 100 milliseconds for everything else. This matters because it's polling every single device here, every loop, and trying to see if there's data. If I made the timeout too long, it would take way too long for it to go through everything, and updates would be extremely slow. But I don't always want to update super fast. Let me show you another example here with a power supply. As this device turns on, we'll see that it doesn't immediately show up in the readings. But if I wait a little bit, there we go, now it has shown up. And that is actually my doing. The power supply here has basically exactly the same issue that the 34401A here has. It goes into a front panel locked out remote mode when it is read. As you can see there, when I was in the voltage set mode, it dropped me back out to the main menu. You can tell that this is because it's being read, because right here's an indicator that will flash, which tells me that it was being read and put into remote mode. Just like the 34401A, as long as you send the IB local command, you can get it back into front panel usable mode. Now, because it kicks you out of the front panel menus when it tries to read the data, I've set it so that it has to wait 10 seconds between pulls so that you have time to try and configure it. Because it does take a little bit of time to set a value here, and I don't want it just getting cleared out every single time. But I think you might start to see the power of what I have going on here. We are currently reading from 3 different GPIB devices all at once over the same bus. And what's really cool is I can turn these off, wait a moment, and those will all slowly go away. What I've created here is actually an overlay that I can put in OBS and have on top of my streams, or record it and edit it in post to have the readings on my video feeds as I'm working. Because
Recording the displays of these devices, especially when you have them on an electronics bench like this, is kind of a pain in the butt. So this is something that I've been wanting to do for a very long time, and it's really nice to finally have this done and working. But I don't just have to tell you how good it is. Let me show you with a real-world use case of why this is beneficial and how having this kind of stuff set up like this can be really handy.
Let's try a real-world example where I'm going to want to see the response between an input and an output. And we're going to do that with this fan that came from the GPIB server that I worked on. This is a 12-volt, 7-amp fan. It can spin crazy fast. And we can power it from this and measure the tachometer with this. So first, I'm going to connect a probe that'll go to the tachometer. Then I'm going to join the grounds between these two devices, so the reference level is the same. Then I'm going to take two very thin needle nose probes and plug these into the power supply so that we can use those to power the fan. Down on the work surface, I'm going to connect these probes into the connector here for the fan power. These are a tight fit, but they do actually fit here, so this will work out well. And then I'm going to stick a jumper wire into the yellow wires position here. And then all I have to do is clip on to that, and we have our full setup. Now, I want to be able to watch this to make sure nothing weird is going to happen, because this thing has enough power to be able to fly off. So I need to keep the camera trained here, but I want you to be able to see the readings, which is where being able to overlay this stuff comes in handy. So I'm going to turn on the power supply first here, and we can see it popped up down here. I'm going to go ahead and edit the overlay in here in post. Now, I'm going to set the voltage on this to 12. But I'm going to leave the current at 0. So the voltage is going to kind of fluctuate as it gets pulled into the fan, but it's not going to move yet. Now I'm going to turn on the 34401A here, which will show up a lot faster. There we are. And I'm going to set it to frequency mode. Now we are currently getting 0 hertz out of this thing. So let's start to ramp up the current. I'm going to set I out to 0.5 amps. All right, so we can see on our multimeter reading that we're getting about 300 hertz there, and the current is at 0.5 amp, and it's drugged the voltage down to 9 volts. So let's set this to I set 0.75 amps. We can watch the speed of the fan ramp up with the current. I'll give the power supply a second to catch up. There we go. So now I'll step it up to 1 amp. We're up to 1400 RPM now. And let's get a little crazy. I set 2 amps. $2,600 RPM, and yeah, it's getting loud. Now, if this were something that I'm trying to film, I might try to put my fluke next to here, but I'm getting reflections and things like that. Or I might have the camera pointed down here and then need to whip it back up here and refocus. And then the display's a little hard to read because it's got the LCD reflection thing going on in the background, but then you might be missing the action. And that is why having the ability to overlay this is so nice, because I can point at the subject, but still get the information. All right, I'm going to turn the power off here now. And there we go. Fan fully spun down. This is just too much fun. And as I turn off the equipment, the overlay will disappear. So nice. Well, I think that's going to be it for this simple video today. That is how I am reading all of my GPIB enabled equipment. Eventually, someday in the future, I might try to look at the oscilloscopes and logic analyzers over that, but that's going to require something a lot more complicated than just reading a simple value and putting it on a web page, which is why I'm nowhere near ready to get into that yet. But for now, this is a massive help, and I am really looking forward to getting this working. I am now waiting for the Linux kernels to be updated on Ubuntu so that I don't have to do all of the kernel module installing. I'm really hoping, knock on wood or whatever, that it's going to simplify that, because yeah, that is a big pain in the butt, but it's so worth it to be able to do stuff like that. Well, if you enjoyed that look at some random GPIB nonsense, you might want to subscribe, because I'll definitely be doing more of that in the future. If you want to help support the channel, you can find me on Patreon, but for now, that's it, and I will see you next time.